RS-485 stands for Recommended Standard and was created by the Telecommunications Industry Association and the Electrical Industries Alliance in 1983. RS-485 is a differential signaling standard which defines the electrical characteristics of drivers and receivers used to implement a balanced multi-point transmission line. The standard is intended to be referenced as the physical layer for higher level standards such as DL-T645, DMX512, Modbus, and others, and is used widely in industrial applications for its robust electrical characteristics. RS-485 allows for serial communication across a multi-point network. Some examples include the minimum required signal amplitude generated from the transmitter side, the input sensitivity of the receiver, and the input impedance of the receiver. Cabling, connectors, and data protocol are not defined in the standard, allowing system designers flexibility. RS-485 is a balanced transmission standard, meaning it requires two signal lines whose voltages are the inverse of one another. This offers two advantages for signal integrity. First, because the two signal lines are implemented with twisted pair cable, noise from external sources couple equally into both signal lines as common mode noise, which in turn is rejected by the differential receiver. Second, because the two signal lines switch inversely to one another, the electromagnetic field emitted by each line is opposite of each other, helping to attenuate the noise emitted. RS-485 supports multi-point bidirectional communication across two wires, which can help lower cable costs. An RS-485 driver is required to drive a large differential signal into an RS-485 load. This enables the signal to travel across long distances while still being large enough to be accurately interpreted by the receiver. An RS-485 driver and receiver are also required to operate over a common mode range of -7 volts to 12 volts. This enables data fidelity in the presence of large ground potential shifts relative to other interface standards, and may also extend the operable distance of an RS-485 transmission line. An RS-485 bus consists of multiple transceivers connecting in parallel to a bus cable. To eliminate line reflections, each cable end is terminated with a termination resistor, denoted as RT, whose value matches the characteristic impedance denoted as Z0 of the cable. This method, known as parallel termination, allows for higher data rates for longer cable length. Figure A shows a typical half-duplex RS-485 bus configuration. A half-duplex or two-wire bus consists of multiple drivers and receivers connected in parallel to a single wire pair. In half-duplex communication, a transceiver may be either sending data or receiving data, but not both simultaneously. Only one driver connected to the bus may be active or enabled at any time. Multiple active drivers will result in data errors and may result in damaged transceivers. Figure B shows a typical full duplex RS-485 bus configuration. A full duplex or four-wire bus is connected in a master-slave configuration, where the driver of the master node is connected in parallel to all the slave receivers on one wire pair, and the receiver of the master node is connected in parallel to all the slave drivers on a second wire pair. Separate bus cables allow for simultaneous communication in both directions between master and slave nodes. The half-duplex configuration is often preferred for its lower cable cost in applications that require low data rates. Full duplex networks can accommodate applications which require higher bandwidth due to its ability to transmit and receive data simultaneously. An RS-485 driver consists of two pairs of transistors and diodes. The logic level on the D input pin defines which pair of transistors are biased when the driver is active and can drive current in either direction of a load similar to that of an H-bridge. The voltage drop across the load resistor measured from pin A to pin B is referred to as the differential output voltage of the driver. Recall that we stated the driver can drive current in both directions. This means in respect to pin A, the differential output voltage can be negative, like in the figure to the right. In the ideal case, the differential voltage of the driver would be the entire range of VCC, but due to the construction of the driver, there are voltage drops across the diodes and transistors, which lower the differential voltage. The overall differential voltage of the driver is therefore the supply voltage minus the two voltage drops of the diodes minus the two voltage drops across the transistors. For an RS485 driver to be within RS485 specification, all drivers are required to be able to generate a minimum 1.5 volts differential output voltage across a 54 ohm resistor. A simplified model for the driver is shown in the figure, where pins A and B generate the voltage difference across the load resistance, but pin A and B are plus or minus half of the difference plus an offset voltage. RS485 receivers attenuate the transmission signals, which are typically beyond the range of the supply voltage of the receiver to levels that are within the supply range. Because of the ground potential differences that may exist between receivers on the bus, voltages as low as -7 volts and as high as 12 volts may appear at the A and B terminals of the device. The attenuation factor is typically on the order of 10 to 1. So the voltage levels that actually appear at the comparator input are within the operating range of the device. The voltage input threshold positive, or VIT plus, is the value above which the receiver output must be high when VID, or voltage input difference, is greater than or equal to VIT plus, or voltage input threshold positive. Recall that the voltage input difference, or VID, is equal to VA minus VB. The TIA/EIA 485A states that the positive receiver input threshold, VIT plus, should be no greater than positive 200 millivolts. The voltage input threshold negative is the value below which the receiver output must be low when VID, or voltage input difference, is less than or equal to VIT minus, or voltage input threshold negative. TIA/EIA 485A specifies that the negative receiver input threshold VIT minus be no less than -200 millivolts. The receiver output state is indeterminate when VIT minus is less than or equal to VID less than or equal to VIT plus. Modern transceivers have a voltage input threshold positive, or VIT plus, less than or equal to 0 volts. This is to ensure that the receiver outputs a failsafe high during bus short, open, and idle events without the use of external failsafe resistors. External failsafe resistors increase the common mode loading on the bus. Therefore, by using transceivers with integrated failsafe protection, offset receiver input thresholds, more receivers may be connected to the bus. During bus short events, the A and B receiver input terminals are shorted together, creating a differential input voltage VID of 0 volts and a high receiver output. During bus open events, the A and B terminals are floating, and the receiver comparator inputs are determined by the receiver input bias network, which are equal, creating a differential input voltage VID of 0 volts and a high receiver output. During bus idle events, there is no driver actively establishing a potential on either bus wire. Since there is no current flowing in this case, the differential voltage across the termination resistor or resistors is 0 volts, creating a differential input voltage VID of 0 volts and a high receiver output. The hysteresis voltage, VHYS, specifies the minimum value of the difference between VIT plus and VIT minus. The minimum value of the hysteresis voltage, VHYS, specifies the maximum value of differential noise to which the receiver is guaranteed to be immune during switching events. TIA/EIA 485A specifies that a compliant RS-485 driver must be able to drive a 1.8 volt differential output voltage across a common mode range of -7 volts to +12 volts with an equivalent load of 32 1-unit load receivers. 1 unit load is equivalent to an input leakage current of 1 milliamp at 12 volts or 12 kiloohms. Modern transceivers have higher receiver input impedance, allowing for more transceivers to be present on the bus. The table shown provides the unit loading, bus input leakage current, and equivalent input impedance for the different receiver characteristics. The bus input leakage current is the most reliable way to determine the receiver loading from the datasheet.